Hi, here is Yuri Muzichenko presenting his inventions. Today I am going to talk about our know-how devices. Here we have a model of 3-phase, 2-circuit, 22 km long power transmission line. The model consists of transformer substation and tower with 6 lines. We have 2 transformers in the substation, main and backup, energized either from a single or from 2 individual lines. In this particular case, 2 transformers, main and backup, are energized from a single line. Let us demonstrate operation of the line in normal 2-circuit 3-phase mode while supplying voltage to the line. As we see, the transformers are on. We apply voltage to phases A, B and C of the first 3-phase line. And we see 3 linear voltages at the first multimeter. Then we apply voltage to phases D, E and F of the second 3-phase line. And 3 linear voltages can be seen at the second multimeter. Connect load 1 and load 2, such as thermal guns. We observe operation of both loads. With load being on, we energize 3 phases in the line. Because of this action, the load 2 is switched off as expected. Now, connect our know-how device to the first and the second 3-phase lines, and that will change property of the line. We connect our know-how device to the output substation, then connect this device to the input substation. Now, disconnect 3 phases of the line in the same way as we did before. As this happens, we observe new fundamental property of the line, which is load continue working. We can keep disconnecting up to 3 phases in the line in any order. The load will continue to be active. These new properties of power transmission line allow conducting corrective and preventative maintenance without disconnection of consumers. Let me demonstrate next fundamental property of the power transmission line: ice melting without disconnection of consumers. With the help of liquid nitrogen, we manufacture ice on the wire of the power transmission line. Turn ice melting mode on. As we see, during ice melting, the load, namely computer, did not turn off. Now we observe temperature and humidity around 6 bars during automatic ice melting mode. It took only 2 minutes to melt ice of -50 degrees centigrade. Next know-how. For better illustration, let's consider performance of asynchronous motor of a new type, motor in the part-phase modes. Connect 3 phases to standard asynchronous motor and connect 3 phases to asynchronous motor of new design. Let's demonstrate performance of both motors in the mode when 3 phases are available. Standard asynchronous motor with power of 10 kW is running. Asynchronous motor of new design with power of 7.5 kW is running as well. We use laser tachometer to monitor motor's revolution. Now, disconnect a phase in the supply circuit of each motor. Turn on asynchronous motor of new design without phase. Motor is working. Turn on standard asynchronous motor. In such operation mode, the motor either fails or will be forced to turn off. Another know-how. Let us introduce a unique phase stabilizer of SFN type that allows asynchronous motors continuously performing, as well as allowing motors to start and slow down gradually during part-phase modes, and with that to work in the energy-saving mode. Let's start standard asynchronous motor of 18.5 kW in the energy-saving mode. We will monitor motor's consumed power by current and voltage displayed on 3-phase multimeters. We monitor currents and voltage of the set mode. The device analyzes operation of asynchronous motor and within time interval of 30-35 seconds reduces power of motor without changing the number of shaft revolutions. We observe reduction of operating current of the asynchronous 18.5 kW motor. Total saving of consumed energy in idle mode is 50%. Let us demonstrate performance of standard and series motor under open phase conditions. Motor continue working, no phase. Stable operation of motor during open phase in the power saving mode. We turn off the device. Let's demonstrate gradual setup of motor without a phase. As we see, the motor is gradually started. Device transmits information about motor status via GSM channel. Moreover, if operator does not make a decision within specified time, it slowly turns motor off to avoid hydro-hammering. Display will initiate open phase. Another know-how was tested on operation of server or small data processing center. We are going to simulate failure conditions in the three-phase grid, specifically loss of neutral or any other phase. In addition to servers, we have plasma panel 150 cm connected to the three-phase grid. As we know, in case of open circuit or short circuiting of neutral in the three-phase grid, the voltage of 220 volts will grow to 380 and by that cause failure of sensitive equipment. We will use Chauvin-Arnaud Measuring Center CA8335 to measure quality of electric power. I'd like to demonstrate that our equipment protects servers from failure, and we will see if open phase would cause servers to trip or not. Observe 3 voltages of the supplying grid. Disconnect neutral of the three-phase grid. No voltage change in the grid. Let's reconnect neutral. Disconnect phase A by 2 single-phase automatic circuit breakers. Measuring center shows no phase A, but computers keep running. Let us restore phase A. Now, disconnect phase B by 2 single-phase automatic circuit breakers. Phase B is disconnected by servers continue running. Reconnect phase B. Disconnect phase C. Observing no phase, but operation of servers is stable. Restore original condition of the three-phase system. One of the most important features of the new power transmission line is protection of equipment against high voltage pulses caused by lightning under conditions of load running. In our case, computer servers. As we see, other equipment, plasma TV, is switched off due to high voltage discharges up to 400,000 volts generated by Tesla generator. However, we can see that the computer connected to power transmission line operated under impact of high voltage pulses is still functioning and processing video signal. Good luck